Well, in this case, right now, we'll just begin with the literature review, just to point some specific interesting points right now. So our first author that we have been learning a little bit of this reconstruction was Kaczmarczyk, I think it's that. Kaczmarczyk, yeah. And he did the first study to describe it, how they can reconstruct the sample, how can they extract the pores, and he created a methodology to do this. So in this case, we are just picking some of these ideas and try to create our own methodology. So in this case, this is the first study to describe the possibility to use ScanIP and Console. In this case, he also used the Aviso Fire software. That in the first stage, I will show on the next slide. In the first stage, he just reconstructed through the CT image that he also using a micro CT equipment. And they reconstruct the first slice and create the 3D model through the Aviso. Then they use the SimpleWare software to reconstruct the interconnected pores, and then they export the STL surface. The surface is just the simple surface that you can create in this kind of software. So in this case, he reconstructing STL format. He exports to Console, and then they make some simulations. In this case, he used the nitrogen through the mesh, and this is the first one that we read. And then the next paper that we consulted, in this case, the same author. Sorry, this is the conclusion that he made. No, volta. One of the most important conclusions is that in the step of model preparation, the downsampling is very important. For example, when they are reconstructing the image, you can get the data with 10 or 20 giga of data. So it's extremely huge. You need to reconstruct with a little bit. You have to be a faster simulation, so you have to get a small area. So in this case, they are studying this downsampling. In this case, they studied the downsampling factor of 3, 5, and 10. For this case, the best one was the factor 3. And the second conclusion that we think is very interesting is that they can also match the permeability results with 2.5 of error, relative error. So in our opinion, it's a good conclusion, and we expect to reach something like this in the future. The other work of the same author in 2011 was the first attempt to develop a methodology with the carbonates, using the X-ray microtomography, with the same microtomography that have been used in the last study. In this case, they also use the 3 downsampling factors. In this case, they also reached with the downsampling factor 3, the best one of them. They also generate the meshes in Console. We intend to do a little bit different. We try to recreate the mesh inside the SimpleWare software, and then extract, import in Console just the mesh, the 3D mesh, and then simulate the single phase or 2 phase flow in this case.
And we're going to use only 2 softwares, not 2.
Yeah, we are going to use only 2 softwares, not 3, as the previous work. And in this case, the first stage is the same one as the previous work. He was working with 3 different samples, carbonatic samples, generate 3 different meshes, of course, and they reach these conclusions. For example, when they do the measures, they get, for example, 1.29 for the porosity, here in this case, and 0.09 for the permeability. The measurement, it's real. In this case, with the simulation, for example, for this first case here, he also found the difference between the real permeability and the simulated one, 0.02, which represents 22% of error in this first one. But in the first one, he's using the downsampling factor of 5. And here 5, and here 3, and here 10. So as you can see, if you use downsampling factor of 10, you have a bigger relative error. So we are focusing in using only the middle one, this 3, the downsampling factor 3, just to improve our results, we think. And then the main results and conclusion they reach is they demonstrate that the resolution of 6 micro is good enough to get the permeability calculations. So we will try to do the same. And the assumption that the rock between the pores is permeable in this work also takes to some error. But we are trying to study a little bit more of this. So in 2010, the same author, they also were studying just how would be the stage to get this X-ray microtomography, how we can handle with these images and recreate the 3D model. So the main problem that he found in his work, they found in his work, was a rupture of the pores connections. For example, here it's the studies of the authors. You can see that, for example, here's the original sample. Here we have the 2, 4, 6, 8, and 10 downsampling factor. So when you're using, in this case, comparing the letter E to letter AE, you can see that a lot of interconnection was not existing anymore. So it's very important. One of their conclusion. Não, pode voltar. Não, volta. One of the most important conclusions that they described in the paper was the process to recreate the image, to process analyzing this all image. So it's very important. It's not a simple task, as is mentioned. Zalewska in 2011 just described the entire process to use the X-ray source to get the 3D image, the reconstruction from this hardware. They also specify the hardware and how to process and analyze the whole image. So we are trying to do the same process with a little bit modifications during the process. And one of the important papers that we have read is about yourself at 2007, when the authors informed that the predictability of these models depend on the accuracy of the complex geometry. So it's very important to work with the most accuracy geometry to reach the best results as possible. And here, just to describe a little bit of their work, they did the 3D images through the micro-CT. They used the black and white to binarize the image. They reconstructed the pores, and then they extracted the connection of these pores, and then they simulate here a pressure gradient. And this is the inlet and here the outlet of this sample. So you can see that you have a pressure gradient here from 2 bar to 1 bar. It's very interesting because it's the first time that we saw they creating a pressure gradient in their work. So here in this case, we just highlighted two more important points. The first one is that the porosity permeability and capillary pressure, they calculate with the simulation. We're very close to what they reached with the measurement. So it's very interesting for us. And the last one, that these models can be used for rock typing, upscaling, or to extrapolate petrophysical properties. And so in this case, they can use to investigate or study some phenomena like the dissolution or precipitation in an CO2 injection. So it's very interesting and can be done in simulation as well. So this is an important paper as well, this 2010 for Bogdanov, when they are studying the pore scale of two-phase flow in porous medium. So this is the first study they are proposing to create a pore scale modeling and then use a two-phase flow inside the console. So the main purpose of the development of 3D model of two-phase flow, and then study the displacement of heavy oil and their problems, the associated problems. So in this case, they create inside the console itself the geometry. They choose what is inlet and outlet, and then they can create the boundaries of the entire geometry, and they simulate in the console. In this case, the viscous limit case, where you have the capillary of 0.50. So it's very interesting because it's the first time that they use the console to do two-phase simulation.
But it's not 3D, it's 2D.
Yeah.
So I think we are going to be one of the first one to perform this work.
In this case, they just presented their solutions with analytic and numeric, and they are very close. So for us, it's very important because they are just exposing the relative permeabilities, and they know what's in phase here. And as you can see, it's very close. So it's very important for us to try to follow this one. And the next slide of Bogdanov of their paper is just the 2D study of the two-phase flow. In this case, they presented three different here. One of the stable drainage with mobility of 0.1. As Santiago has told before, you can see, you can study, and then you can give an idea of how much you can put here. And in the other two cases, unstable with mobility of 300, and the last one at the capillary limit. So it's very interesting because this is all simulated in console, what you intend to do. And just to highlight the main results, for me the most important is the last one, when they try to show that the realistic geometry, of course, it becomes of the key factors of such a modeling. So for us, it's very important to get a real high quality reconstruction of the interconnected pores. And just to finish, is the last one of the literature review. A very recent paper of 2014. It's a possibility to upscale the results based on a well-defined structure of how we can work with the results of the small sample to upscale, which is quite possible, but it's necessary some efforts on this, which is possible. And other very interesting work is Narcillo in 2009, when he was working with upscaling of Navier-Stokes equations to pores medium. So, and the last one is, of course, a list of papers that is very interesting and you use as well to create our studies. Well, just to present the first step of our project, we have to get the CT image from the real cores that you can see here. And as Thaís told before, this is the paper presented for von Bigling in 2008, when he compares the real sample of pre-salt area to analog pre-salt carbonate that in this case from Lagoa Vermelha, which also we have a stromatolite. And here's the reconstruction of a CT image. And this is ours. In this case, we are using two CT equipment. The first one is the Phoenix from GE, when you can reconstruct, I try to describe shortly two positive points and two negative points. The first, for example, we can reach an excellent or good resolution, depends on the power you use in the machine, in the equipment, and the possibility to study medium to big samples. Now, in this case, as you can see, it's a sample around 20 centimeters in height, and I don't know, 10 centimeters in the diameter. So it's a medium big sample, yeah. The problem is the big data set that you have. For example, if you studying this sample with the best resolution, you can get 60 giga for just one measurement. So it's very complicated for us. And the second one is the possibility, if you're not using the best resolution, to lose some of the connected pores, which it's very difficult to happen when you use the micro CT equipment. In this case, this is the two samples that we have here. We have reconstructed there in the simple air, and as you can see, you can separate a region of interest here, when you can make we can study the pores inside them. For example, here we have the micro-CT equipment that we also are using. And we have this stromatolite here that's from a work of Borg and Patrick. Yeah, in this case, as you can see, it's a sample of 1.5 inch. It's a small one, yeah. And this is the original formation when it's been studied in IDC base in Bahia State, here in Brazil. And we also reconstruct there in simple air. But as you can see, it's a sample of 1.5 inch. And there we have a sample of 20 centimeters. So it's very different. You can choose, but it depends on a lot of factors. Just to point to positive to negative as well. Excellent resolution, of course, it's depends on the equipment. In this case, in micro-CT, the possibility to improve the reconstruction. It's a positive point as well. And the biggest problem is here, the small samples. Because sometimes you cannot reach the REV. It's the representative elementary volume, yeah. So that's a big problem, but in this case, we're just studying how to reconstruct and how to extract the pores and then simulate. So for now, we are not so, yeah. Here, just to compare the two equipments, just to most important points. The first one is the maximum object size, 27 millimeters in diameter and 50 millimeters dependent. In this case, we have 60, 100, and 300. So it's very different. And in this case, we have the detail detectability of 0.5 micro. And in this case, down to 1 micron with micro focus, or 0.5 if you are using nano focus. So it's very good. Here, just to point some shortly how we can recreate 3D images here in simpleware. In this case, we are working with a coquina, and then we can reconstruct the 3D model of the entire sample. The first step is this one. Then we can crop a cuboid, select from the entire sample. We can select a small one, or depends on what you want. Then we can select what is pore and what's not pore, what's rock. So it's it's a turning point, because if you do not select the correct one, you can choose, you can change rock to pores or vice versa. So that's the problem. So in this case, we are using some tools that's possible through the software, that's stress holding or flood fill. In this case, there are a lot of studying in this area. One of these we are using here, the phase mean thresholding. That's the best one. And as you can see, you can reconstruct them, the entire pores. Then we can resample. For example, when you are working with a sample with a very resolution, the data is too huge. You have to work with a file that's not too huge. So we are working here to resample with a downsampling factor of 3. Then we can reconstruct the interconnected pores only. We have to do some of the work inside the pores, because sometimes they can not be together. The rupture inside the pores, that's the problem. But with these tools here that we presented in the software, it's quite possible to almost reach the original one. And then we can work and separate the interconnected pores, generate the mesh through the FE tool. And this mesh here represents the interconnected pores of that's real rock there. So in this case, we are trying to work with a mesh not so big, because we do not have a software too powerful. But we think that the size that we have created here, something around 300,000 mesh, it's quite good for us. This is yeah. So in this case, we have imported to Console, that's the multi-physics simulator, the mesh of the interconnected pores of the real carbonate sample. So it's our first step when we reach this was very good.
Now talking about Console with Physics, it's a software that can model and simulate any physics-based system. So you can use to perform simulation in electricity, magnetism, chemical, whatever. We are going to use the subsurface flow module that can model subsurface flow in channels, saturated and variably saturated porous media. In our case, we are going to use a stationary model. And then we are going to import the image from Simpleware to Console to perform a two-phase fluid flow simulation. Here we have the window from Simpleware, where William did the image processing and extract the pores. And here we exported to Console. And then we have the Console image, the pores extracted with the inlets and outlets defined. So to reconstruct the structure of pore network allows use of the Navier-Stokes equation to simulate fluid flow through the pores without any experimental data, like we have to do in Darcy's law. So the equations used in Console are going to be the porosity, that we are going to calculate from the tomography, the permeability, the Navier-Stokes simplified, because we are going to use this stationary model, and the permeability calculated from the Navier-Stokes equation. That's going to be this one. Here we have the Fourier article. He worked with Simpleware and Console too, and he performed a simulation through 3D axis, X, Y, and Z. We are going to do the same thing in our work. We are going to perform the 3D simulation. And here we can see the results in Console, and we have the brighter the colors, the higher the velocity of the particle. Here we have the massless particle trace through the soil sample. And to conclude, this study aims to create a reservoir characterization workflow methodology and calculate petrophysical parameters of pre-salt analogous carbonate samples, such as porosity and permeability. This methodology is applicable to all carbonates, although we are going to work with lacustrine carbonates. It's going to be possible to compare results from the simulation done with the same stromatolite sample using different kinds of tomography, the Skyscan, GE, CT equipment. In general, hardware density is important to simulation speed because you have to simulate in a time period. So for the studies, the hardware is very necessary to decrease simulation time and allow to work with more complex samples.
Just to finalize here, we have some problems and challenges as well. The first one is the problem with the results. In this case, we have to work with the image. It has to be a great work, because if you do not work properly with the real core, you do not have the interconnect ports. So that's the first problem. The second one is probably the hardware that we necessary to simulate. I don't know, 1 million meshes. So that's the other problem. It's the hardware itself. But we also have some challenge that's very interesting. The first one here is to perform the two-phase flow. It's an attempt to do the first time. Yeah, it's not so easy. The second one is to apply the methodology to your in the near future. I think it's a great challenge, especially for the lab, I think. The other one is to create this methodology. It's to improve the results. When we started this work here, we just do not know about downsampling. When we saw that the simulation that we are trying to perform was too long, we used the downsampling factor. So now we are trying to discover some new challenges inside the methodology itself. So for us, it's also a challenge. Yeah?
In other words,
it's very necessary to do the downsampling because of the time of the simulation, but we can't do the downsampling with less resolution, because we can lose the porosity of the real sample. So I think that's it. Thank you.